Okay. So, I'm recording now, and let's get started. We're gonna start with the questions from the quiz that was on Thursday, I believe. So, someone sent a question in the quiz in the chat, and they asked to go over the retrosynthesis from the quiz. Um, oh, this is funny. He had to make his own key. Okay. All right. So the retrosynthesis is question number 2 on the quiz. So let me just start sharing real quick. Okay. Can you guys see my screen now? Okay. So the retrosynthesis from the quiz. So this is quiz 2. Quiz quiz 2. Question number 2. We start off with a benzene ring, and we end up with a benzene ring that has 3 things on it. One of them is CO2H, one of them is NO2, one of them is Br. So when I look at all of these 3, they all have something in common. Aren't they all deactivating? I mean, I'm not totally sure about this one because I haven't memorized the sheet, but aren't they all deactivating? Is CO2H deactivating? I don't have the list open either.
It is, yes.
So they're all deactivating, but there's going to be different levels of deactivation. So I would say that the most deactivating would be this one. Let's start with the most activating. So the most activating would be BR, and then the second would be this, and then the third would be this. So going off of that, we're going to have to make sure that we don't, like, for example, first, because if we add the NO2 first, it's going to be really heavily deactivating. But one thing I'm thinking is, like, so the BR is, it adds to a pair and ortho position. So that's kind of helpful because if you look at the BR, NO2 is ortho and the CO2H is para to that. So it kind of makes sense that BR would be our first, right? But another interesting thing is that we don't even know how to add CO2H directly on. The only way to do that is to add like some kind of alkyl group and then use like Na2Cr2O7 to change the like regular carbon alkyl group into a CO2H. So, and since this, okay, so this one is meta directing, as is this one. But so if we add, so I'm going to erase these numbers first. So if we add this one first, then we could add this one second or this one second. It doesn't make a difference because either way, you know, they're going to go to ortho or para. But I think that adding this one second makes more sense. And I'll tell you why. Because this one is more activating, so it'll help this get into the meta position. So that reaction is more likely to happen than if you added this one second. Yes, this is also meta directing, which is great, but it's so deactivating that the reaction is less likely to happen. So there's a few reasons why you'd want to go for the CO2 second and this one third. I think at least. Oh, wait a second. He didn't do that on the
The way,
on the
yeah,
thing.
the way
Yeah,
it was
sorry.
done in the key, it
Yeah.
was
Because
with an R group.
yeah, so because when you add it and it's an alkyl first, so this one, because when you add this and it's an alkyl groups are actually way more activating. So this is going to be our number 1. So I forgot that. Because I was looking at all of them, like NO2, CO2H. I was looking at all of them, but in reality, we're going to have to add this one as an alkyl group. And alkyl groups are the most activating, then Br, then NO2. So that's why we're going to go ahead and start with the BR the alkyl group first, because the alkyl group is most activating. So if we start with an alkyl group, so you can just add whatever you want. I'm just going to add something like this, and AlCl3, or no, sorry, that won't work. Let's just add this. And then what happens is that this is going to go to that position, right? We're adding a methyl there. Next, what are we going to do? So we're going to leave this as a methyl, and we're going to put our Br on, because again, like an alkyl is so activating. So we leave it as a methyl first, and then we're going to change it to a CO2H afterwards. So we can do a Br, Br2, Fe, Br3, and then that will promote this Br going to the para position. And then after that, we're going to have to change this to a CO2H at this point before we add the NO2 on, because otherwise it would be like a really messy retrosynthesis. So we're going to have to take this and do like a Clemenson, or no, sorry, not Clemenson. We're going to do our Na2Cr2O7, oops, O7. And that will take this and turn it into a meta-directing group, which will help our NO2 come to the right position. So then our last step, I'm going to erase everything. Our last step is to just add our NO2, so that's just nitration. So you just go, oops, sorry. So you just go NO3, yeah, you go NO3 or HNO3. Just put my H at the end. And H2SO4. And so that'll add a nitration to that specific spot. Can you do the, no, you cannot do the, someone's asking if you can do your, like this, if you can have your methyl, and then can you do NaCr2O7, and then, which will get this here, right? And then can you do your Br? No, because just look at it for a second. If you left it like this, first of all, it's really deactivating. Second of all, it would be much more likely to go to a meta position, which would be here, instead of where it's supposed to be in the para position. So that's a no. Does that make sense to the person who asked? Okay. Any other questions about the retrosynthesis? When you do your retrosynthesis, it 100% has to make sense. That's very important. Okay. So, I guess there's no other questions about the quiz then. So, I mean, the key is pretty good because Dr. San wrote it himself. If you guys have any other questions that come up, then let me know. So, just for a second, I'm gonna move on over. Actually, one more thing. Does anyone have any questions from the exam now? From the practice exam? I know a lot of you probably didn't go over it yet, but just keep in mind that our exam is coming up. It's going to be on Thursday. And so it's going to be kind of, for most people, it takes them about anywhere from like 3 to like 7 days, I want to say, of prepping for an exam. And so if you're someone who it takes like on the longer side, like closer to like 7, like a week, then you definitely need to get started ASAP because it's coming up very soon. And we're having a lot of weather issues, clearly. But I wouldn't count on school being canceled on Thursday, although it seems like a possibility. Jay, do you have a question?
Yes. Can you explain question number 3 on the exam? I gave the same answer as the person who did the key. I don't understand what the difference is.
Exam question 3.
Question 4 on the exam. What is the
Oh,
major product when HBr is added to the double bond of the following compound? Explain why your expected product is major.
okay. All right. So, let's see. So basically, this is, I can explain like what Dr. San meant by his correction. So what happened is that we have this thing, right? I don't know how else to describe it. And so this is reacting with HBr. This is question 4 on the exam. So when it reacts with HBr, you're gonna have to think about like what's gonna happen where is BR gonna go? So first of all, you did the correct thing by thinking that, what's gonna happen is that this is gonna reach out and it's gonna grab a hydrogen. BR is gonna break off. Now, what does that give us? It gives us this molecule that looks exactly the same as before, but what happens is that it now has a hydrogen on this side and a plus on this side. Why did the plus go to this side? Because it is the benzylic position, so it must come here. But this is not the end of the story. What he's saying here is that the BR doesn't just come and sit in this position. There's actually another position that's very stable for it. So what's more likely to happen is a rearrangement, and that's what he's showing. So he shows that this double bond from up here comes down and takes care of that positive charge so that the new positive charge appears in an even more stable position. So the new position is going to be up here, and we're going to have a double bond here and a double bond here. So in this way, we've maintained like a lot of our conjugation, but we have a positive charge that's like very, very stable. It's allylic to two different double bonds, and it's kind of like, I don't know, it's also tertiary, so there's like a lot of things that make it more stable. Does that answer your question? So normally when the correct answer is that it becomes benzylic, it's just one benzene ring. So there's nowhere for anything to go. So usually, like, if he gives you a double bond like this and he says react it with HBr, then what you would do is you would say, yes, the Br is going to end up on this carbon right here, which because it's benzylic. That is correct for this situation. But in the above situation, since a rearrangement is possible, that makes it into a tertiary position instead of being secondary, and it's still very, very stable because it's surrounded by double bonds, then that is the correct way to do it.
Okay, so then where does the BR go?
So the Br would go here. It would be more likely to attack once it gets there.
Oh, okay then. The key was not super clear about what the final product was, so that's good.
Yeah, I don't really know. I mean, yeah, he really wasn't. I think that's where the Br would be. For
Thank
sure.
you.
No problem. Because if you think about it, there would be no reason for any rearrangement to happen past that. This is the most stable it could get. All right. So any other questions from the exam? And I understand that, a lot of people haven't gone through it yet. So we will go through I'll take more questions from the exam on Wednesday, and we'll possibly even just go through some of the stuff on Wednesday as well. But since a lot of people haven't done it yet, I don't want to go through it yet because that'll kind of like ruin your study plans. Okay.
Oh,
Mm-hmm.
I did have another question, but it can wait until tomorrow.
Oh, no. You can go. You can go for any questions you have now. That's totally.
Oh,
But I didn't want to just like go through the exam right now because a lot of
oh.
people.
So
Right.
the double bond on question 7M is in kind of like a weird position. Um,
Okay.
yeah. And I want to know, like, why is the double bond not connected to the place the OH was?
Um. I
Like,
don't.
why is the double bond there?
Yeah, that's a good question. Let me take a second to just look at this. Okay. Yeah, and then H2SO4. So it definitely needs to eliminate, and I personally kind of disagree almost with the answer key. So I would ask Dr. Son about that. Because I kind
Okay.
of disagree because of Zaitsev's rule. I think it would be more likely to be just right there. I don't really see why it moved. There doesn't seem to be any logical reason for that. So it looks like a mistake.
Okay.
Because you'll see
Thank.
how like he accidentally moved everything over a little bit too
Oh,
to the
maybe.
right. Yeah,
Yeah.
so it looks like it's probably a mistake. I don't understand. If there's a reason for that, let me know. But it looks like a mistake.
Thank you.
No problem. Any other questions? Okay. So I'm gonna let that go for now. All right. we'll go back up to February 4th. We'll finish February 4th, and then we'll do some exam review if we can. And our break is going to be at 7 o'clock. 7 to 7:10. All right, so here is a very, very good summary. Whenever he does these summaries, please sit down and memorize them. A very good summary of how to kind of use Grignards. And so he has like lots of different options for how it works and stuff. So I guess I'll go through it just to kind of explain, because sometimes people don't really get it after looking at this kind of stuff. So here is RMGX. What does that mean? That means that basically the X stands for any halogen. Usually we do a BR, right? We do MgBr. So I'm going to just change this to BR to make it easier. And R stands for any kind of alkyl group that you could have attached to the MgBr. Now, the first thing we have is MgBr with H3O plus. So what that does is it basically takes that R, the H donates, the H3O plus donates a hydrogen towards the alkyl group, the MgBr comes off, so all you get is RH. Now, I'll do a quick example of that because that might not make a lot of sense. So let's say we had MgBr attached to an ethyl. So once I add that with H3O plus, what happens is that a hydrogen goes and it will attack this, and that MgBr will be able to come off. So what we get is we simply get an ethyl, okay? Or CH3CH3 is basically what we get, an ethyl. Because at this point, basically before we had CH3CH2 MgBr, but now it's grabbed one more hydrogen to this position, so we get CH3CH3. Okay? And then while I'm going, just let me know if you have any questions. So that's the first thing. Now, let's say that we react it secondly with HCHO. So what is HCHO? HCHO is basically, it looks like this. It's a carbon with a hydrogen, and it has a double bonded oxygen and another hydrogen. Okay? HCHO. That's basically what it is. So when we react something with HCHO, as you know, let's take again the example of that ethyl that we had from before. It's going to attack here. This is going to go up, and it's going to create an OH. Okay? So that's why for the answer, he says that it makes R, whatever that R was before, and now it also has that carbon attached to the two hydrogens, but that O is now attached to a H of its own because it becomes an alcohol. All right. Next. So in this situation, it's kind of the same thing as above, but instead of, and let me just redraw this as it is, because like that'll be helpful too. Okay. So in the next situation, he kind of draws it out instead of making you kind of figure that out. But this is an R, and this has a hydrogen. So what happens here is, again, our ethyl is, I'm just going to be using an ethyl from now on as our R, attacks there, and what it does is it creates an OH as well. So what we're going to have is, and let's call this R prime because we need to be able to separate the two. So we have our R prime just like before, we have our hydrogen just like before. Our ketone now becomes an OH. And we've also attached our ethyl, which I'm just going to call R because it's the R from there. Okay? So that's that. Next, we have and this is all stuff that you definitely 100% need to know for the exam. Ketone, but this time it's R prime and R double prime. Okay, so what does that mean? That, again, just imagine our ethyl attacking. Just always imagine like some little ethyl attacking. And what that's going to do is that's going to create our R double prime and then our R prime, just like what we had before. And our O is going to become an OH because we've attacked it now. And we're going to attach our regular R that's attacked it, which is our ethyl in this case. Next, we have something that is basically, it's a ketone, but this is an OR, so it's more like an ester, and this is our R prime. So what happens, or I'll call this double prime because I need something. So what happens is that um, our ester can kind of break off when we attack it. So our ethyl attacks the carbon, and then this is going to break off the ester. So what we get is, and then there's no need for this to become an alcohol because our octet isn't broken. So again, we're just going to have our R prime on one side and our ketone at the top. And then instead of our OR, the ester, you can just replace that with R, which is the thing that, oh, just a second, sorry. What is, do you guys understand what he's drawn here? Looks like I did something wrong. Oh, I think he's showing that it got attacked twice. I'm so
Yeah,
confused. Um,
it's
once it
reacting
hit
with
a point.
2 moles.
Yeah. So this is after 1 mole. So I'm just going to show you guys both of them though, because oops, let me just leave that. Okay. So that's after 1 mole. So after 1 mole, what we get is we get the R from the MGBR, and we also get our R prime, and the ester has completely cut off. Then we can do that one more time. Oops. We can do that one more time with an R, with another one. Let's say it was the exact same thing, R MGBR. And so in this case, that's finally when we can't break off an ester or anything. We can't break off a leaving group. So what happens is we have our R prime, we have the R from before, we have our O, which has turned to an OH, and then we have the new R, which has gotten attached. My pencil just died. So I'm going to have to talk without drawing for a second. But basically, because there's no ester that can break off, in the second time we do that round, we're going to get 2 R's attached to it. Okay? So, like that. Next, any questions so far? Because I'm going through this kind of fast. But you guys have already seen this stuff before. I just want to explain the drawings so that when you see it, it makes sense. So next we have something with where it's R. No, yeah. So it's reacting with R primes, triple bonded CN. So in this case, what happens is that we get. Wait just a second. This isn't making a lot of sense to me. Is that a C or is that what? Okay. All right.
Um, these are not on the exam, but um, it's basically like a cyano group, right?
Okay. Yeah, but I'm confused about where the ketone came from. Like, where did an O come from?
I have no idea, but it's on the next exam.
Okay. All right, so we're not quite there yet. So let's just ignore all that. And just the last one that's in blue. So this is an like an epoxidation type question. So what happens is that our ethyl will simply attack one of the carbons. And what that means is that the carbon that it attacked gets the ethyl attached to it or whatever, R. And the other one, it kind of like breaks off from there. So what happens is that this breaks off a little bit and it creates an OH kind of. Okay. So that's really how the epoxidation works. And we're going to be doing a lot more about that on the next exam too. Or the third exam. I don't know. All right. So any questions about this? All right. So I'm just looking through this stuff. There's a lot of, stuff that's very repetitive of what we just did. He's using it as examples. And I mean, I'll just go through the ones that I think are especially maybe tricky, that you need to see them in order to know. So here's the good old one. It's basically um it's disguised. This is an ester, really. So he's reacting this with 2 moles of CH3 and GBr. So that's just an ethyl being added, methyl, sorry, and H3O plus. Okay, so here's what's gonna happen. Or actually, let's ignore the H3O plus. So what's gonna happen is that the first mole of ethyl to attack, right, CH3, when it comes, it's going to attack this, and that's going to break off the O, right? So then the second one is going to come off and attack, and that's going to create the up situation where it becomes a hydrogen, an OH. So I think the H3O plus, let's see. So what basically is going to happen is that we have gotten, let's count our carbons first. So there's 5 carbons in this whole chain. So I'm going to draw 5 carbons. And then what I'm going to do is the first carbon, I'm going to make that the one that had the ketone on it. So it's going to have an OH and it's going to have 2 other methyls coming off of it. That's the first one that had the ketone on it. Next over, you have carbon, 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 all the way till the end where you have an OH attached to it. And that's it. Really. Okay, any questions? And I believe he may have made a mistake here. Let me check real quick. Yeah. Guys, do you think he made a mistake here with the number of carbons?
Some days you cannot count to 10.
Yes, there is a mistake there. He lost a carbon. But, yeah. Some days you cannot count to 10, some days you can't count at all. Some days it looks kind of similar, so you don't really see that there's something missing. But there is something missing there, I think, in terms of carbons. Um, yeah. Am I right? Sorry. This is page 2, the end of page 2 of the February 4th notes. I think so. Okay, anyways, there should be 5, 6, 7. Yeah, he's missing a carbon. Okay. Anyways, so let's move on. So that one's kind of tricky because, again, you don't want to miss your carbons. Definitely count, count, count. Make sure you get it right. Okay, here's a cool one. So this is kind of a throwback to something we did in exam in Orgo 1. So we have this molecule, and it's going to look familiar to you because this is OTS, which we will never forget because it's just very interesting and very complex looking, but it kind of looks cool on paper, but it's not even that hard, so it's nice that way. So then we have our CULI or cupric thing going on. So what happens here? So what I want to remind you about this whole OTS situation is it's just a leaving group. It's just a leaving group. It's not a big deal. This whole thing, you could treat it like it was a BR sitting right there, really. So what's going to happen is that when something attacks, something is going to attack this carbon right here, and the whole thing will protonate. It's such a good leaving group. All right. So that should just jog your memory about what OTS is. Another way we can write it, we can just write it more simply if you start getting confused because it has like so many moving parts. Just write down OTS like that, okay? So then you know that this entire thing can protonate. I've seen people make a lot of mistakes where they protonate after the O. No, no, no. OTS. O is part of the word of the leaving group, so O is also going to leave. Make sure you protonate for the O. Don't protonate, after the sulfur or something, or something like that, So, anyways, this is gonna protonate, and the only thing, so we can just think of that like it was like a BR or something, and then this again, like all you have to do is think of this thing as a nucleophile. So this is basically gonna look like that. It's kind of a propyl that has a negative charge on it. So the propyl is gonna come attack the carbon right before the OTS, and all we're gonna get is we're gonna get the same thing but it now is attached to a propyl. So 1, 2, 3. Okay, yeah, so that looks right. Questions? Be familiar with OTS because it probably will come. You cannot forget what OTS is. If you have any questions about specifically like old things from Orgo 1 that like I'm just skimming over real quick, but like you're not that comfortable with, then just come to me, let me know, shoot me an email, something like that, because we can work on that. I also do have I do tutor on Tuesdays, private sessions, so that's totally a possibility. If you're someone who wants a little bit more specific, directed personal work, then you can just let me know for like a one-on-one session, or I mean, you make an appointment. Um, but yeah, so we can work on like older stuff if you're having issues with that. So then he had just some more examples with leave-in groups and Kubrick. So, one of the coolest questions he's going to ask you guys is one where you have to figure out what was the Kubrick component, what was the CULI component. So this example is like kind of fun right now, but maybe not so much on an exam. So the question is, what we're using here in order to create something where the I left, and what we have in its place is this. So all you have to do, it's pretty simple, is count how many extra carbons you have. So we have 1, 2, 3 extra carbons. Make sure you count this third one. I feel like a lot of people are gonna be like, oh, that's not extra, it's only 2 extra. No, it's 3 because this was an I. So, basically, from here, you just need to attach those 3 things to a CULI. So just inside of a bracket, write, you can write down, you can make it this easy, and then you can do CULI and a 2. Or you have the choice of writing it more as a condensed formula if you find that easier. But again, like when you're doing it as a bond line structure inside the arrow, make sure you do it right. So this is 1, 2, 3 inside of the bracket, right? So you have to have 3 carbons, exactly 3 inside the bracket, and then this other bracket closes before you get to the next joint, kind of. And going back to if you wanted to do condensed instead, you would do CH3, CH2, CH2, and then you'd close that. 2 of them is ULI. So those are your 2 options. All right. So what else do we have here? This one might be worth doing. So I just want to remind you guys a little bit about, you guys did this on your quiz, but I just want to remind you guys a little bit about how to get an MJBR going. So here's an example that he has in his notes. So basically we're going to react this with PBr3. And so what that does, like, let's just go through this step by step. So it's PBr3, then Mg over Et2O, and then another one is going to be, this is our Grignard, and then there's an H3O plus, finally. So let's go through step by step because he didn't. He only showed the final product, but I'll walk you guys through everything. So the first thing, PBr3, what does that do? It just changes an OH into a Br. Perfect. Now, the second step is MgETO to Et2O. So what it's going to do is it's going to change this to an MgBr, and that's it. Now this is ready for Grignard. So we take this basically, what is this? This is essentially, let's change it into our nucleophile. This is essentially this. And when you look at it, there's going to be like no rearrangement happening here. So this is just going to attack that carbon. Now, what does that do? So I'm just gonna I'm gonna draw the bottom component like it is. The top component had been like this, right? But when this carbon attacked here, this becomes an OH because it would break octet that way. So what we get is we get this bottom component. I'm not really good at explaining this kind of stuff, but it's attached to here, and then there's like, I don't know. Like, I'm not that good at explaining like exactly how to get here, but you'll probably be able to figure it out. It's kind of going to look like that. So, I mean, in the end, you might just want to count your carbons real quick. So, going back here, we had 1, 2, 3, 4, 5 carbons, and then here we had 1, 2, 3, 4, 5 carbons, right? So altogether, we should have 10 carbons. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That makes sense. Um, yeah. So I think one thing that I would remind you is that you can't really like take away or add new carbons, so to speak, with these reactions. Yes, you're adding carbons in that we went from 5 to 10, but I mean, they all came from somewhere, you know? So you need to make sure that there's no carbons that came out of nowhere. They should be either from the original, the one that's attached to the MGBR, or they should be from the one that's the actual Grignard. Same with oxygens. You shouldn't have any random oxygens. You should just have the one that came from the ketone and any other ones that might have been attached to the thing in the beginning. But this OH, for example, got turned into a Br, so that's not going to be in our final product. So make sure that your answer makes sense and that there's nothing random or new in it. All right. So here's an interesting, I'm not even sure if I can do it. So let's see. But if I don't know how to do it, then we can tackle it together. So we've got, all right. So this is what we have, and we're reacting this with NBULI and ET2O. And we also have, it's going to be a Grignard type thing, and H3O plus. Okay, my question is, for me, this looks a lot like CULI. What's the significance of the NBULI? What does that do? Okay.
Isn't it the thing that just adds lithium to the end of an ion? So like as opposed to like, Greenyard being MGBR, BULI, I thought just switches out the hydrogen in the CH with a lithium.
A lithium on its own?
Yeah, like not a Greenyard lithium, like just a lithium.
Okay.
I
So,
could be wrong, but
no, someone else in the comments said that it's essentially also like a strong base that takes the hydrogen out. So that kind of goes, that makes a lot of sense. So I guess what we have in between is we somehow get to this position where this is now a nucleophile because of a hydrogen being removed, possibly an Li there, but you know, that's kind of like a spectator that will leave as soon as it sees this Grignard situation here. So it's going to go attack. And then from here, we're just going to have something where, um, in order for it to attack there, this is going to be interesting. In order for it to attack there, it needs to kind of break that O. So this is what we originally had, and this now becomes an OH. And then attached to that, we're going to have a carbon that's triple bond attached to this. And then, of course, you should draw it out like a little bit nicer if you have time, but this will do the trick. So it's just a way of making this into another nucleophile. All right. Um, so here's an interesting thing that I like. I don't want people to get caught up or like caught off guard if something random happens like this on the exam. So this is another way that like I don't know if I've seen it before, but very good to keep in mind. Another way that he can kind of ask you certain things. Um, so in this situation, he has an HCl first. So what does that look like? That looks like probably a Cl going to this position because of Mark's rule and all that kind of stuff. Then after that, we're going to have an Mg. So what this is it's going to be an MgCl instead of an MgBr. So I just wanted to bring that up because I don't want anyone to get thrown off guard if something like this happens on the exam. And then this is just going to be, that's equivalent to um, this with a negative charge here, which is going to attack the underside of the ketone. So then we're going to get this, and the ketone is now an OH, and it's attached to this, blue, blue, blue. Okay, like that, kind of like that. Or 1, 2, 3, 4, yeah. No, that's extra. Okay. Yeah. So it's gonna look kind of like that. Wait a second. That's not what he has at all as his answer. There must be a rearrangement somewhere. No. Mm. Sorry, I just need to figure this out for a second. If you guys see where I went wrong, then let me know. Okay, that's it.
Isn't
Yeah. So,
there? Yeah.
yeah. So this is not a carbon, that's just a hydrogen. So, yeah. If you take that away, then I have the same answer as him. All right. So, and I just want to draw it nicer just for the sake of it. So this is 1, 2, 3, 4, 5. So we have a chain of 5. And then the second to last one has an OH on it, and the one right before that has a methyl. So that's it. Okay, retrosynthesis. You guys always like doing retrosynthesis, so let's go for it. Because these retrosynthesis are definitely different than the stuff we've tackled before. I think this might be the first day that we're doing retrosynthesis that's not really just that whole like ortho para activating deactivating stuff. So this is what we have. Now, first we're gonna so we have to figure out how do we add. If you think about it, we've only added one more carbon and an OH. See? One more carbon and an OH. So I definitely think that this must have come from something that was a ketone and it had a hydrogen and CH3. Or sorry. Nope, that's wrong. It came from something that had 2 hydrogens on it because we only added 1 carbon. So this is the 1 carbon that we added up there. You see what I'm saying? So since we only added 1 more carbon, that's the carbon we added. So there must have been hydrogens on each side. Um, so yeah, so like how are we gonna do that? So like some simple ways of doing this, like first we need to change this into an MGBR because then we just need to attach it with this thing and it's over. So it's not a complex reaction at all. How do we get a BR there? We can do HBr, but we need to make sure that the BR goes to the right, not to the, we want the BR to go here. So that means it needs to be anti-mark because mark, the hydrogen, would go to the place with the most hydrogens, and the for anti-mark, the hydrogen would go to the place with the least hydrogen. So we kind of need that Br to end up there. So for that reason, we're going to do Br2, and we could do like H2O2 or something like that. H2O2 is my favorite. And then, or sorry, not Br2, HBr. Sorry. Um, Okay, so what this does is it adds a BR to the correct position, which is here. Then we just need to do our Mg and Et2O. And one like hack, kind of like a life hack, is just you can add them both in the same step almost, like I've done this before. So sometimes I will just go like here, and I'll go, okay, I'll just do it all in one step. So I'll do um, HBr over H2O2, and then I'll do Mg over Et2O. And then I'll just be like, okay, there. Just get it all over with in the same step. Because it's such a pain to keep doing like the Mg second. So you can do this if you prefer. Next, we're finally just going to do our last step. So this last step, like I said, it's an ketone. Oh god, it died again. A ketone, and then just leave your H3O plus in the bottom, and you get that answer. Questions? All right. So I'm letting. Sorry, just a second, guys. Okay, guys, sorry about that. Again, because of the snow, like I couldn't drive back to school, so we might have a few interruptions, to say the least. Okay, so this is the second one. Um, Also, remember that you guys need to know your names, your common names for this, right? So, quick question, refresher. What's the name of this? Have you guys been keeping up with your naming? Isn't there a name for this with the double bonds?
We have not learned the name for that one. The one that's like
Oh,
where the that's a just a regular cyclohexane.
oh yeah, no, no, but let's say it had like a benzene in it.
We still do not know that name yet.
Oh, okay, okay, all right, cool. Then let's just do something else. What's the name for this in the chat? Cool. What's the name of this? I'm gonna search up some more to ask you guys. Yes, good job, phenol. So the first one, sorry, if anyone's confused, the first one is toluene, and the second one is phenol. And then, okay, here's another one. Um, what's this? Anisole. That's anisole. Um, what's this? Those are the harder ones. Aniline. Yeah. What's this one? This is the one I was thinking of. Styrene. Yeah. So toluene, phenol, anisole, aniline, styrene, and then we have some other ones which we're going to do real quick. So this, what's that? This is benzoic acid because it's an acid. What makes it so acidic? Resonance. As soon as you see this resonance situation, you know it's a benzoic acid. Does that help you remember? Benzoic acid? Yeah. Because if you take away this hydrogen, then we have a negative charge here. It's going to be back and forth with those two, with the double bonds. So this is very, very acidic. It looks a lot like, acetic acid, right? What's acetic acid? Um, Let me see. Acetic acid, yeah. So acetic acid is just this. So that's like another way you can know it. So this is just acidic. It's an acidic molecule to have. So when we have it like this, it's called benzoic acid. All right, here's another one. What's that? See, this looks like benzoic acid, but it's not benzoic acid. Yes, this is acetophenone. Acetophenone, okay? And then finally, we have one more, which we need to do. The other ketone one. What's that? Benzaldehyde. Good. Yeah, benzaldehyde. All right, good. So, yeah, so we've gone over all of them. Make sure that you know this. I'm going to erase all this. Let's get back to our retrosynthesis. Um, okay, so for this retrosynthesis, um, if we look at it, so if we think about in terms of how many carbons have we added, which is probably the first question you should always ask yourself. Because when we see this alcohol, we kind of know that it was a Grignard situation, so we just need to figure out like how exactly did it work. So let's call this carbon 1 and call this carbon number 2. So basically, so JD says, fun fact, styrofoam is made from a styrene polymer. So just think like that. Somehow styrofoam is made from a polymer, including all of or involving this molecule. That's fun. All right, so let's call those carbons 1 and 2. Now, if we look at it, let's say that was carbon 1 and that was carbon 2, because they don't have to remain in the exact same orientation. Then that means we've attached two more carbons to it. So that means this thing is all the new stuff that we added. So what does that look like? So we need to have the one carbon that the ketone is coming off, and we have to have another carbon there, so that's a CH3, and then we have one hydrogen. So that was the, what do you call this thing? Like there's another word that's not ketone. You can't really technically use the word ketone, and my teacher Govin used to get mad at me all the time for saying ketone when it wasn't. There's a word for like a double bonded O, whereas a ketone is necessarily like this. It has to be like that. But when your double bonded O is like in different positions, aldehyde, maybe? I don't know. All I know is that I never really listened to him. I just kept saying ketone. Um, because isn't an aldehyde a very specific way that a ketone is?
Aldehyde is the one that you just drew. I just know that that's the name of
Yeah.
that molecule.
Carbonyl, that's what it is. Carbonyl, guys. Yes, that's the word I was looking for. So carbonyl is a general word you can use for this right here. Double bonded O with a carbon right underneath. It has nothing to do with what's on the right, what's on the left. Aldehyde is necessarily like this. Aldehyde has to have a hydrogen on one side and something else on the left. But carbonyl is a very general way of saying it could have anything on the right, anything on the left, right? Dr. Son doesn't like using this word a lot, but some people will be more particular about that. Possibly, so Govin was, and then possibly Dabra as well. So carbonyl means that this part, carbon with a double bond and oxygen, whereas aldehyde has to involve this hydrogen on the right. It has to have a hydrogen on one side. So carbonyl is the correct word that I might start transitioning to say, because ketone is technically something else as well. Ketone is really very simply, it's kind of like a carbon on each side. That's a ketone, I think. So anyways, going back to that, we kind of need to know what kind of group our carbonyl is on. So what does that carbonyl group look like? How many carbons does it have? How many hydrogens does it have? So that's why that's the first step that I do. Then after that, we just need to figure out how are we going to get, you know, how are we going to get our MGBR into the position that we need. So I'm thinking yes, because MBS is going to add a bromine to the benzylic position, right? So if we do MBS, we're going to get like this, a bromine right here. And that's perfect because that's what we need. We need an MGBR coming off of this carbon exactly. Okay. So if it was a different position, we'd kind of be in a mess because we need to figure out other things, like other ways of doing it. If we needed a MGBR on this position, I would probably do MBS, then do elimination, then do anti-mark HBr to get a BR onto that position. So it's just a little bit more complicated. But in this situation, it's easy. We just have to do MBS. And then from there, we're going to do MgET2O. Gosh, I hate doing this. I wish there was a way of doing it way faster. Anyways, so we got this MGBR. And then finally, we just have to react it with that and also H3O plus. That's it. And also, something he really cares about is you have to put your numbers for the Grignards. If you're not going to do two separate, so one option is you could do this, and I'll let you guys go in a second. If you're not going to go like this, MGBR, and then if you don't drag them out in two steps, then you have to put your numbering, okay? So your two options are to leave it as two steps, clearly, or you can do both of them and make sure that you number them to show that you understand that one must come after the other. They can't both be dumped in at the same time. Okay. All right, so we're gonna get going now. Let's meet back at 7. Let's make it 7:15. Okay. All right. So let's move on to another retrosynthesis. So we had just finished the first retrosynthesis of, or no, the third wait, second retrosynthesis of the February 4th lecture. So let's move on to the third, page 6. So we start off with a benzene ring, and this is going to become a benzene ring that has, oh, this is something that we need to know. D, which stands for a dense hydrogen, basically. Just think of it as D for dense, and it's a hydrogen that's particularly dense. And I'll show you how to do this. It is one of the Grignard reactions, though. So firstly, what's going to happen here is that this is a combination of the two things we learned. So the first set of retrosynthesis we've been doing have been dealing with, activation, deactivation, stuff like that. And the second set of retrosynthesis we learned had to do with Grignard. So I'll just show you how to do this one, and if we get to another one, then you can do it along with me at the same time. But this is really a combination of both. So some of the things we need to think about are, first of all, the way that we add this is going to be through a BR being there, with an MG and stuff like that. So firstly, let's start with adding that alkyl group, and I'll show you why after a second, why it's important to do that. So we're going to add the alkyl group, which is basically this. Um, and what happens here is that now this is going to, it's just going to attach like what we, regular alkylation of a benzene ring. And the cool thing about doing this first is now we can add our BR on really easily, because our BR we're just going to do like BR2 over Fe BR3, and that gives us something in the para position, right? Because there's a little bit of stereohindrance here. So this is perfect because now we can just change this BR into an NGBR, and then we can do Grignard to get our D. And I'll show you afterwards why it's necessary that we did this order. Okay, so here we have, the same thing, but this is MGBR now. And finally, all we have to do is we have to take this MGBR and react it with D2O, D2O, which is basically water that is called dense water. It's water that has the hydrogens on it are dense. So when you react an MGBR with a molecule of dense water, D2O, then you just get a D instead of a hydrogen there. So let's talk a little bit more about the order. Why couldn't we have made our D first and then did alkylation? Because then it wouldn't have guaranteed that the alkyl was exactly para to the D. So it's very important that first we did alkylation, then we did bromination, because that guaranteed that the alkyl and the bromine are exactly para to each other. We could have done bromination first, but bromine is less activating than an alkyl group. So that's why it's necessary that we did alkylation first. So let me just explain a little bit more about what I'm talking about. So in red, I'm going to do some examples that we shouldn't do below. So what I'm saying is we shouldn't do first bromination, then do alkylation. Because this is less activating. So this is going to be less yield because it's less activating. Okay. And the other question is, why can't we do why can't we form that whole D and then do alkylation? Same thing, because this D isn't para-directing, it isn't anything. It's like a hydrogen. So it doesn't direct to anywhere. So the alkyl would end up anywhere in relation to the D. So let's say that we had ended up with our D first. Like we had gone through the whole steps of like BR, bromination, then MGBR, and then, turning that into with using the Grignard. We can't then do our alkylation because it would go all over. We would get alkyls here, we get alkyls here, we get alkyls here, here, or here. They could equally go anywhere. All right. Does that make sense? Yes, you are expected to know D and D2O. You definitely need to know this for the exam. You'd probably get like 1 or 2 questions, or I don't know, like max like 1 or 2 questions with a D in it, but you definitely need to know it, and it's super easy. It's just D2O, basically water and a Grignard. That's it. All right. So let's go on to the next one. So this is a carbonyl group becomes methyl with a double bond there. So basically, I think the best thing would be like if you look at this, there is an addition of a carbon, right? Where is the addition of the carbon? This. This is a new carbon that we've added. So kind of making this into an OH and then eliminating it would work. So what I mean by that is let me actually take a step back. Let's start the way retrosynthesis is supposed to work is that you start from the right, but the retrosynthesis they give us in class are so short that we can usually do them from starting from left to right. But the way it's supposed to work is you're supposed to work backwards. So what I'm saying is we could have H2SO4 and an oxygen that we eliminate to do that double bond. Now, from here, how do we get an oxygen in this position? Well, I think it would be like one step basically. So we would just have a methyl with MGBR on it. Is all. And then we need H3O plus. Right? So those are the only steps we need in order to create this. So first, a methyl is attacking that ketone, and then we're using a H2SO4 to eliminate it. All right. Next, so here we have just a second, sorry. Oops. Okay. All right. So now we have benzene ring that becomes sorry, just a second, guys. Sorry about that. So benzene, can you guys see the screen? Yeah. Okay. So benzene ring becomes same thing, but it has all this stuff on it. There's a lot. All right. So how do we get this whole complex thing going on here? Well, let's look at addition of carbons. So which carbons are new? This, 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 and this. And there's an OH there. So this tells me that we must have come from something so that's 4. So 4 carbons, and there must have been a double bond on a double bonded oxygen on one of them, right? So then when you attack something here, that would make an OH, and it would look exactly like that shape. So you basically, the rule of thumb is you take all the extra carbons and then figure out what kind of carbonyl they must have come from. All right. So taking that information, all we need to do is simply make an MGBR group on over here that would attack the ketone. So first I'm going to start off. I'm going to do this all in one step because I'm getting really tired of this. So the first step would be um, BR2, oops, BR2, FE, BR3. And then the second step would be MG. Oh my god, my cat is jumping around. If you guys hear him, he's just jumping around because he thinks he's seeing something. All right, so and then that's ET20. And what does this do? This is just going to give us an MGBR in the correct position. Then from here, it's just like one more step. So we're just going to take that ketone that I created above, and we're going to do H3O plus or H2SO4, whichever one you prefer. That's necessary, and then that's the answer. And again, like you want to check your shapes afterwards, make sure that it ends up being the right thing. Okay, so that's that for this. After that, he has some questions. Do you guys have any questions from the review questions at the end of the lecture on February 4th? Because like he has like a list, like 2 pages of questions that, I mean, I can go through them. Maybe I could do every other one because we have half an hour left. Or I was thinking about switching to the exam review problems, which he posted for February 9th. So let me know in the chat which one you prefer. Do you want to switch to the exam review questions, or do you want to stick to from February 9th, or do you want to stick to the questions at the end of February 4th? Oh, JD's asking the cat to say hello. Unfortunately, he doesn't really say things. He like barely ever meows. Only when he's very hungry and he's getting his food in the morning. Okay, so someone said exam review. I've only gotten one vote so far. Exam review or February 4th review? Okay, I'm gonna go ahead and I'm gonna do February 9th because I'm gonna assume that you guys went over the February 4th questions. And okay, so someone asked a question from February 4th. All right, perfect. So yes, if you have any questions from February 4th, let me know, but I'm gonna assume you guys went over those, so we'll do February 9th for now. Because next time I see you, it's only gonna be the day before the exam. Unless I decide to add an extra session, we'll see about that. 5G, okay, so question 5G from February 4th. Go all the way down to page 8. If you're trying to follow along, all the way down to the end of page 8 is 5G. All right, so what do we have? Okay, here is a ring, a cyclohexane. Okay, so this is reacting with, okay, he's sitting right down in my lap right now. Okay. All right. So my cat's kind of in the way, but we'll try to do this. So excess CH3 okay. So let's just look at this for a second. So this is kind of, it's kind of like wordy almost. So let's just redraw it for like, sanity's sake, into something that is much more sane. This is basically what that is. Like, there's no need to do that whole like trying to figure out what this is. Like, just draw it as a bond line because that'll save you so much effort. So he's saying that there's excess of this though. So I'm gonna write X to show that there's excess of it. And also H3O plus. All right. So what's gonna happen is that basically this is gonna come along, and I don't have the answer key with me, but this is gonna come along and attack here. And I think that it can only attack once. So even though he says excess, we're only going to be using 1 mole. So basically, our answer is going to be the entire original thing. But this O has turned into an OH. And we have now attached this. Is that the answer? Because I don't even know where to find the answer.
That is not the answer.
Okay.
This is actually the same. Oh, well, this is actually the same thing that I was talking about before, where if a thing is protic, and it's being reacted with a Grignard, it's just like MGBR attached to where the OH is now, except without the
Oh,
H, and then like a
oh,
hydrocarbon. Yeah.
because I forgot one of the most essential parts. I just noticed it just now. He wrote at the bottom, he wrote ether. Yeah, he wrote ether as the solvent.
Yeah, so actually OH, the original molecule is protic, right?
This.
Yeah, that. It's protic. It ends
Well,
in an OH.
yeah, I guess. Oh, yeah, that's true. All the
So
other
that's why
do have
so
just an
that's why
H or a
that
carbon.
answer you gave was not the answer. I also fell into
Yeah.
this pitfall.
Okay. All right. So that makes sense. So what Julie's saying is that since it's protic or since it's aprotic, sorry, which is but also the ether is aprotic though, right?
Yeah,
Ether
the
is
ether is aprotic. It's just
yeah.
like if there's anything protic.
Oh, okay. All right. So if there's anything protic, and that would involve because like if we remember our list from Orgo 2, which I don't really have in front of me, but your list from Orgo 2, protic stuff was a lot of stuff with OH in it. So it was like H2O was in there because it has an OH. It was like, like it had like ethanol, it had methanol, lots of different things with OHs. Those were all called protic, okay? Let me actually leave that. So this is a list of example protic solvents. So anytime you have a protic element in your thing, then the MGBR basically switches to that protic OH. So here, this is what's creating the protic elements here. So our answer is going to be this, from what I understand, from what you're saying. It's going to be this, where the MGBR goes into the takes the protic thing.
Well,
But
with
someone
the
said that
O
there's
still
two
there.
answers.
Well, with the O is the other O is still there, like only the H gets replaced.
Oh my God. Yeah, I've seen that before. Okay, never mind.
Yeah.
Yeah. Okay, but someone's saying that there's two products in the answer.
Yes, and the other one is the thing that's in MGBR, that like the thing that's attached to
Oh yeah, this.
MGBR.
Okay, yeah.
So it's
Yeah,
just
yeah.
like CH3,
Yeah.
CH2, CH3.
Yeah. Okay. So yeah, that's the other thing because like the MGBR clearly left this other one. Oops. It left this molecule right here to go on to the other one, so that's just going to be left without an MGBR. But it also doesn't have a negative charge because it took that H. So essentially what happens with when you have something protic, I just want to reiterate everything. So what happens is that this hydrogen right here goes into the position of the MGBR, and the MGBR takes the position of the H. So that's why in the end, we have the situation where the hydrogen was, we now have an MGBR, and where the MGBR was, we now have a hydrogen. Okay. Does that make sense? So the one way that I want to kind of contrast this with all of our other problems to really illustrate what's going on here is in all of our other problems, you'll notice that it was like this, and it had a double bonded O and a carbon on the other side. Or it would have, something like this, and on the other side of that ketone there was a hydrogen, or on the other side of that ketone there was an ester. So those are the three options we had been familiar with before, either some other kind of carbon alkyl group on the other side, or a hydrogen, or an ester. So that's why when you see when you see an acid, okay, this is an acid, it's double bonded O with an OH right next to it. Whenever you see an acid, then that's the situation where you give up a hydrogen, because let's think about it. What does an acid love to do? And this is a very strong acid, by the way, acetic acid. I mean, it's not technically a strong acid, but it's very acidic. So what does an acid love to do? It loves to give up its hydrogen. So this acid, ketone with its OH, is very acidic. It loves to do resonance. It's going to give up its hydrogen, which is going to leave it with a negative charge, which is what it loves, because now the resonance can go back and forth. Does that make sense? Yeah, so that's what JD is saying too. She's saying that this is basically an acid-base reaction. Okay. So I guess that kind of clears it up. I again like the whole product thing is very important too, but like this is really just a strong acid and it needs to behave like a strong acid. Now from here, now this can be used from here in another reaction possibly. So that's really important, and thanks for bringing that up, because that's definitely a tricky question. And definitely look out for that on the exam because he will throw one or two in. All right. Um, if you guys hear someone snoring, that's my cat. All right, so let's go on to the exam questions now. So what this is when I went to the February 9th lecture, I saw this thing called exam review problems. So I'm, I don't know, does anyone have any questions from here? Because if you don't have any questions from here, then I'll probably just go over like every other question until the end of this session. Or like just look for ones that look especially complex. All right, I'm just gonna go ahead and get started. So here, this first one is already looking really appealing to me because this is a cyclicization question. Um, so basically here, and he will always tell you, by the way, he will say cyclic before he gives you a cyclic question. So please don't worry about that. That would be very nerve-wracking to think that he could just like throw a cyclicization question in there and not let you know what it is beforehand. So this is what we're dealing with here. I don't like this at all. All right. Methyl. Oh my god, guys, it's so cute. He's snoring like in my lap right now. All right. So, this is okay, and then we're reacting this with ALCL. Um, so this should scream alkylation to you because, you know, AlCl3 and the fact that we have a Cl here, that's exactly how alkylation went. And we have a benzene ring, so it works out perfectly. But really the question is, where is it going to go? Because you have to look at all your groups and see which ones are most activating, blah, blah, blah. So the most activating thing on the ring, so the ring essentially has two groups coming off of it. Everything coming off of this carbon would be group number 1, and everything coming off of this carbon would be group number 2. Now, group number 1 is primarily like a nitrogen-based group coming off of the benzene ring, and group number 2 is more like an alkyl-based group coming off of the benzene. So what is more activating? The nitrogen, right? Because if you look at your list, this is going to be more activating than a plain alkyl group. So for that reason, this alkylation is going to happen either at an ortho or para position to the nitrogen. So clearly the easiest way is because this ortho position is already taken. This ortho position is so far away. Clearly the easiest way to do it would be to attach it to this para position. So that's why the answer is just it's kind of going to be like, it's kind of hard to draw, but okay. So it's one. I'm going to count the number of things in the ring because I just want to figure out the general shape of it. So it's going to be 1, 2, 3, 4, 5, 6, 7. Okay, it's going to have 7 things in the ring. That's a lot. All right, so I'm just going to go off like this. That's 1, 2. Oh my god. 1, 2, 3, 4, 5. Okay. This is going to have a ketone on it, and then one more. I think. Guys, just ignore me for a second because this is taking a little bit. I think it's just like that. I don't know. Yeah, I think that's it. Because that's 1, 2, 3, 4, 5, 6, 7. Yeah. Okay. So that's the answer. It's pretty terrible. um, any questions? Someone said, can you count starting from the other side of the nitrogen? Um, could I count what starting from the other side of nitrogen? I'm a little confused. Um, oh, yes. So when you're determining the ortho or para position, yeah, this is something that I think I mentioned it, but you might have not caught it. So when you're trying to figure out ortho or para position, I'm just going to do this in blue. So the nitrogen is clearly the boss, right? So that means it's going to be either in this position, which is ortho, or this position, which is ortho, or this position, which is para. So this ortho position, the one at the top, is already gone, so it can't go there. And then between ortho or para here, it's going to be much easier for it to go to the para position because it's closer. Like, imagine it going all the way across to the ortho position. It's going to be really hard to draw and stuff like that. So just do the para position because really you can do either. And of course, like we always have that situation where the ortho position is going to have difficulty with hindrance. So going para in this position is definitely the easiest all around. Because, like, imagine trying to draw it in the ortho position. And when I was counting, I was just trying to figure out, like, approximately how many carbons needed to be in that ring that we were forming. All right. So I'm gonna skip the next one because we kind of already talked about that. Um, well, actually, no. Let me bring this up real quick. So, this is an example where I kind of just want to bring up something we talked about earlier because it really all ties in. But here is an OH, and we're doing H3O plus with this. So what's going to happen is that we're going to eliminate it to the benzylic position so that everything is conjugated like this. And that is the correct way to do it. It's all conjugated now. But I just wanted to contrast that with a reminder of something that JD brought up earlier, which it was really like complicated and really good to know this. But it was basically, what was it? It was a double bond in this position with HBr, and the answer was that actually the Br ends up all the way over here because of rearrangement. And we have here, let's say it was double bond, double bond, double bond like this. So we have a rearrangement where a new double bond goes there. We have double bond and double bond. Okay. So I just want to bring those both up. So the first example is an elimination, so it has to go to a conjugated position, and there's no rearrangement in this situation possible. I mean, if you think about it, like you're not going to be able to rearrange this. So that's why, that's definitely the answer. And then for the second one, there is a rearrangement happening with that carbocation. All right. I'm just going to continue doing every other one. So here's this one. And this is reacting with NBS. So the principle with NBS is that your bromine needs to go to the most stable position possible. And so for this, that would be an allylic position. Now there are two possible allylic positions, right? The one possible allylic position is this position, and the other one is this. But clearly this one is the correct one to go to because it's not only allylic, but it's also tertiary. So this is the correct answer. E. So here we have benzene. Okay. Now this is reacting with Na2Cr2O7. So what that's going to do, it's going to attack all of our alkyl groups, cut them off, and put a CO2H in place. So that's just going to be like this, and you have to put CO2H, and then here CO2H. It doesn't matter whether there was like lots of other carbons, you just go straight to the benzylic position and put a CO2H. Now this one stays exactly the same, doesn't get affected at all because it's not an alkyl. G, and you're definitely gonna have to go through these yourself because I'm doing every other one, so there's definitely gonna be like weird ones that I'm skipping. Okay, so for this one, okay, so sorry, it looks a little weird because I don't like drawing my cyclohexanes this way. I like the point to be at the top. So anyways, we're reacting this with, oh my god, okay, so HNO, NO3, and H2SO4. So this is just nitration, and we have to figure out where is it going to go. So in this benzene ring, we have a deactivating Cl. So that's not very good because the Cl is deactivating. So when you compare that with the benzene on the right, it has two alkyl groups, and alkyls are activating. So it's going to prefer to go to the right because the right has two activating groups, whereas the left only has one activating group and one deactivating. And then between that, there's no position that's going to satisfy both of them. All right. So what do I mean by this? Like, this is actually a pretty bad reaction, I think. There's no position that can satisfy both this alkyl group and this alkyl group because they are para to each other. So, you're gonna end up messing with something somewhere. So in the answer key, I don't really know why he would be prompted to do one over the other. Does anyone have any ideas? Because in the answer key, he goes here. But I don't want to, I'm just gonna.
Isn't it because that space is the least sterically hindered?
Oh yeah, that makes sense. Okay, yeah. So
Wait,
instead of going, yeah,
repeat the question.
what do you say?
Like, what was the question about why it goes there?
So I was kind of thinking to myself, why would it go to this position when, I mean, this alkyl is probably just as activating, right? So what would prompt it to go? It can't go to para of either. What would prompt it to go to ortho of one over the other?
Well, I thought Cl like a halogen is deactivating.
That's true, but Cl is all the way over here on this benzene.
Right. So wouldn't it make the whole benzene basically deactivating while
Yes,
that
that's
ethyl
true.
on the
I had already kind of stipulated that this benzene would be a no. It's this benzene that we're talking about. Why would it go there instead of here?
is it not the same molecule regardless? Or am I like
No, that's not the same. No. Look, this is this is 1 over and this is 2 over. I don't know if you can tell because of like my whole like messy drawing, but do you see that?
yeah, then isn't the other one meta?
Well, they're both meta to something and ortho to something else.
Oh, okay, got you. Okay, I get it.
So I was kind of just thinking to myself, okay, why did he choose one or the other? But JD had a good point. Hindrance, like this group right here has a whole like benzene attached to it as well. That's very hindered compared to just a simple ethyl. So we're going to choose to do ortho to the ethyl instead of ortho to the benzene group because the benzene group is going to create some hindrance there. So that's kind of the rationale that I think makes most sense. Okay. Let's do I. All right. So here we have a benzene ring with an F and a benzene ring with a CH2Cl, Cl, and this is reacting with AlCl3. So what's happening here is this is really alkylation, and this is our alkyl group that is getting added to this benzene ring. Now F is deactivating, but it's ortho para directing. So we're going to get the option of putting it ortho or para. Either way will work. This molecule doesn't really have any hindrance happening. That's just a fluorine. So it really could go either way because there's no hindrance. Like if you have an alkyl group with any sort of branching on it, then you might prefer to do a para. So, and especially if he says two products, then you're going to want to do two. So basically we're just going to take this benzene with its fluorine on it, and to the ortho position, I'm going to attach like something like this, basically. Or I'm also going to do it to the para position. So that would be all the way across here. Okay, that's it. HI. Okay, now we are going on to question number 3. So for 3, this is something that I talked about earlier. There's an O there. Okay, so here we're reacting this with a methyl that has an MGBr, but it's actually 2 moles. And H3O plus, of course. So what's going to happen is that the first one is going to attack, and that's going to break the ester. So we're going to get, we're going to get 1. We did this exact thing just like a few minutes ago. Okay, so we're going to get 1 attacking, and then we're going to get another attacking. The first one's going to break the ester. The second one's going to turn into an alcohol, blah, blah, blah. Okay, end of the day, the important part is that our chain was 1, 2, 3, 4, 5 long. So we're just going to do 1, 2, 3, 4, 5. And then the first one is just going to have an alcohol on it and the 2 methyls that we attached. Then all the way till the end, the last one is just going to have the OH on it. That's it. All right. 5. All right, so here we have benzene ring, tert group, methyl, that's para to meta to that. First, it reacts with Br2, FeBr3. Then it reacts with MgBr. Oops, sorry. It reacts with MgEt2O. Then it reacts with HCHO, which is basically this. Then it reacts with H3O plus, which is whatever. Okay, so Br3 FeBr3. Br2 FeBr3 is going to be bromination. Where is it going to go? Well, it's going to want to accommodate both of those alkyl groups. So I think it will likely go to this position. So you're gonna, when you're looking at this, you're really gonna see 2 positions stand out for you. This one or this one. Or this one. So this one, let's start with this one. This one is para to there and ortho to there. So good. It's fulfilling both of them. This one is ortho to there, but it's very hindered because it's right next to a tert group. Same with this one. It's para to here, ortho to here, but it's right next to a tert group. So the most preferable one is going to be here, which is para to the tert group and meta to the methyl. So that means that we're going to end up getting our, and I'm just going to do both steps in one because like I hate doing them individually. Such a waste of time. But we're going to do MGBR. So I'm just combining both these steps together. So MGBR is going to be in that position most likely. Now next, we're just going to do our Grignard. So that's just gonna basically attach an OH onto it, a carbon with an OH. So after following that next step, we're gonna get this. Oh yeah, methyl. Okay. And again, like I'm leaving the question like that I've worked on just now, like I'm leaving it on the screen. So like if you still have any questions, you can send me a chat or open up your mic. All right, here is going to be a really good review. Let's just do this as our last question because it's already 7:56. This is going to be a really good review though. So which of the following is aromatic? Okay, we need to do this. Very important that we touch on this stuff again before the exam because we likely forgot a lot of it. So okay, so for this one, first of all, let's just do some quick recollection of aromatic. So we have three different categories. We have aromatic, anti-aromatic, and non-aromatic. All right. So aromatic means that it follows all of the stipulations that we have for aromaticity, which includes like conjugation, being a ring, having, being planar, sp3, but it also includes the stipulation that it has to have 4n plus 2 number of pi electrons. The anti-aromatic is just 4 pi electrons, 4n pi electrons, and non-aromatic means it violates some other rule, so it's not conjugated, whatever. So, which of the following are aromatic? So I think that you guys can send me in the chat your solutions to this. Um, okay, so you guys are all saying the middle two. So you're saying that number 1 and number 4 violate the aromaticity rules. And let's just go through that real quick. So what does a positive charge mean? That means that it doesn't have any like electrons there. So it's going to be it's gonna violate our, what do you call it? It's gonna violate our number rules. So this is just 4n. Oh, it died again. So the first one is 4n, so that would be anti-aromatic. Second one is aromatic because the negative charge means that it has a lone pair there. So that not only completes the conjugation, but it also makes it so that it is 4n plus 2. So this is aromatic. This one, this middle one, is also aromatic. Okay, but here's my issue with the middle one. I don't really believe that it's aromatic because it's not really 4n plus 2. Actually, it is, if n was 0. Okay, never mind. So yeah, it is. I don't know. For some reason I had this thing where I thought that it had to be at least 6, but I guess not. It's possible for the n to be 0. So this one follows the, so again, what I mentioned about positive charges, you can think of them like they almost skip. So it is still conjugated. Even though it's double, single, single, that positive charge makes it almost like a skip. So it really is conjugated around this molecule. So this makes it aromatic. This one, it's a negative charge, so that means there's 2 lone pairs there, and that makes it 4n, so this is anti-aromatic. This one's also anti. Because again, like I said, positive charges make it skip, so it still stays conjugated. All right, so that's it for today. Definitely check out February 9th, when you get to it. The fact that he uploaded it now makes it easier for you to get ahead on it. And then on Wednesday, we're going to go ahead and I'm going to take questions from the exam. So definitely go over that before our Wednesday session. And I'm also going to probably go over some more questions from February 9th because there's a lot going on there. All right. And then definitely check out the February 4th questions at the end of the lecture because I won't be going over them. I'll just be taking questions if you have them. And then keep an ear out. I might be adding a session. I don't know, maybe like Monday or Tuesday, I'm not sure. But yeah, keep an ear out for that. All right, guys, you guys have a good night. Study hard.